Okay, so last time we started looking at some basic C++ programming, right, just to get you guys kind of up to speed on the syntax of C++. Again, if it went a little quick, I understand it is quick, but I promise you'll get plenty of practice as we start gradually introducing you to ROS. So while we're learning ROS, you'll also kind of get more experience with the C++ as well. So before we get going, is there any questions you guys had regarding setting up the computers and stuff? Is that all going smoothly? Okay, I'll assume it is. So before we get back into the code, we're going to take a little bit of a detour here and start kind of show you guys how the repository is set up and how you can pull the changes I add to the repository and merge them with whatever changes you've been making in the meantime. So we're going to start by opening the file browser here, and if you go in this ROS folder, if you ran the setup script that's in step 2 of the computer setup guide, you should see these 3 folders and this .catkin workspace. So catkin is the build system that ROS uses. So we'll talk about that more when we get to ROS things. Build and devel are again 2 ROS-based things. Build is where all the binaries go, and devel, other stuff goes into. So basically, all the code is actually in this src folder. So if you go through homework 1 and do all of the, making a fork of your repository and pulling it, you should see these 2 folders in your ROS src. So inside this UGV course code are a ton of packages. So these are all ROS. This is all ROS software that I wrote to basically provide you guys. So this is where all the simulation things are based on. So if you have some time, you can go through here, but there's a lot of stuff to talk about before you'll fully understand what's going on in there. But just so you know, that this UGV course code folder is kind of the stuff I'm releasing out to you guys to use for the homeworks that are coming up, and also your projects down the line, to provide a baseline for you to get going. So now, this actually shouldn't be here. I got a little ahead of you guys, so I'm going to just delete these real quick. Actually, just these 2. So this cmakelist.txt is an auto-generated file that gets run whenever ROS is compiled. So for now, just ignore it. So again, these 2 things are kind of automatically provided to you. Now this UGV course is your working directory of your fork of the main repository. All right, so inside of here, you'll see your homework 1 folder. So this is where you do all the things for homework 1, of course. But then you might also see these 2 things here. So this .hgignore, if we look at that real quick, this syntax glob means, so glob is kind of like a wildcarding format. So like, for example, if I say *tilde, any files that start with a tilde are ignored, which means when you go to add files to your repository, Tortoise HG won't show those as options to add to your repository. So same thing with all of these things. So the reason this kind of thing exists is that you don't typically want to put big files in your repository, because then every time you go to pull, right, it takes a long time to download everything. Another thing you don't want to put in your repository are build files. So basically temporary files that the computer will automatically generate based on the source code. You don't want to put that compiled output in the repository because it's not needed and adds extra size that you don't necessarily want. So all of these entries are different types of build files or large files that we don't want to add. This HG folder is going to look very weird when you open it. There's a lot of weirdly named files in here. You should never touch this folder. This is kind of the infrastructure that's behind the whole Mercurial version control system. It's basically what lets you switch between all the past revisions without needing anything. So essentially, this contains the information for any past version that you've committed to the repository. So again, so you don't want to mess with this, and you didn't have to mess with this either. I'll add whatever is necessary to the ignore file. So now another thing you might notice is that some things have a leading period and some things do not. So everything that has a leading period is technically a hidden file or folder. So just like in Windows, where you can have some hidden files, in Linux, that is just it's known by just having a period in front of it. So when you run the setup script, I automatically change the settings so you can see the hidden files, because there is a very important hidden file that we do have to use. But if you go to edit preferences, if you uncheck this show hidden and backup files, those will go away. So they're important, but you don't necessarily have to look at them all the time. So that's why they're just hidden files. Also, if you delete or destroy this, otherwise destroy this .hg folder, your whole repository is dead. You have to pull a new copy from the server, and any changes you made before pushing, that will be gone. So, well, not gone, they'll still be in your actual folder, but you have to be careful to not accidentally overwrite them if you pull a new repository. So again, so just to, avoid these two things for the most part, and you should be good. So now, so those of you who have access to the repository, which I'm still waiting on a couple of you, you might have seen that I pushed some changes yesterday. And basically what I did is I added the C++ files we were working on Monday. So if you go into Tortoise HG, open your repository and click this pull, right? So this will pull changes from the central repository where I put the stuff from last lecture. And I already did this, but I'm just going to go through the so you type in your Bitbucket password in here, and you should see something like this. So again, to review, this top line is your working directory, which means it's the current state of the files on your computer. And this revision number 1+ means that it's currently based on revision 1. So this revision 2 that's kind of branching off here has no effect on the current state of the file system. Which makes sense, because if we go to the actual folder, we just see homework 1 here. We don't see anything that I added here. So to see what was changed in a revision, you click on it, and then down here in the in this window here, you see that I updated the hgignore. I added a couple things to it that we don't want to be polluting our repository, and then I also added all of the files that we created last time. Right, but again, just by pulling, I didn't actually get these files yet on my actual computer. Well, technically I did. They're in that .hg folder somewhere, kind of compressed up and encoded, right? But the actual files are not visible yet. So to make that happen, again, you right-click the version you want to update to, and then click Update, and then click Update one more time. And now our working directory is based on version 2, and that folder appears on our actual computer. And you'll see there's all the all the files that were added. So now let's say you made some changes based on revision 1, like for example doing homework 1, you would have made changes. So for now we're going to update back to version 1, right? And that folder goes away because it doesn't exist at this point. And now we go into homework 1, open the assignment, and then do exactly what you're supposed to do on homework 1, add some text, save it. So now if we look at our working directory, we see, well, again, remember, always click refresh if you go back to Tortoise HG. See, we have a modified file here. So right now what'll happen if we try to update to this new version that I pushed last night, it's going to come up with this message here. So it detected uncommitted local changes. That means it saw that I either modified a file or added one or even removed a file that I haven't committed into a new version yet. But I'm telling it to update. So most of the time, if you just click merge, it'll figure it out and do it successfully. The only time it will fail at that is if you changed this, you changed a file that I also changed in my revision, and it's what's called a conflict. Then you have to do some fancy things. But I don't think that's going to be an issue, because I'm always going to be pushing new things into the repository, and then you'll be potentially just modifying what's there already. So hopefully that won't happen, but if it does, and you have problems, just let me know and I'll try to help you fix them. Okay, so now what you'll see is now our revision is based on 2+, right, as opposed to 1+, but our change is still there, right? So it kept our local changes, but it just merged in all the new stuff that I added last night. So now if we go back here to assignment.txt, our stuff is still there. All right, so that's going to be a very common procedure. You know, basically every lecture I'll be pushing changes with whatever we did in class, and then you'll also be in parallel doing your homework. But again, those should be two separate things. There shouldn't be any conflicts when you do that. So basically, whenever you get an email from Bitbucket saying that I added stuff to the repository, just do exactly what we did here. Come in, do the pull, and then right-click the one you want to update to, click Merge, and then if it says it detected uncommitted local changes, just click Merge, and it should figure it out. So basically, your end goal is to have a straight line here on the graph. You don't want to, if you have any kind of hanging, little branches on this graph, that's not what you want. You want everything to be one continuous line of updates. Now, here's one more thing though, is for homework 1, you were supposed to commit to your repository, right? So what's going to happen is, I don't want to, this is the actual repository, so I'm not going to actually commit it. But if you commit it, you're going to make a new revision, number 3, right? And then you're going to pull in my revisions from last night, number 2. So now that's what's called having multiple heads. There are 2 head revisions that are both the most current, right? That Mercurial doesn't allow that in most cases. So in that case, what you have to do is merge the 2 revisions together. And to do that, what you would do is right-click this and say merge with local. So again, so update just updates your working directory to the state of that revision. And if you have any changes currently uncommitted, it'll keep those. But if you have 2 completely committed revisions that are in parallel with each other, they need to be merged before you can push. Otherwise, there's multiple heads and it won't let you push at all. And so in that case, you want to use this merge with local. And if you do that, well, again, I can't really do it right now, but I think I talk about this in the tutorial document. Let's check. In this Mercurial Concepts PDF. Guess not. Okay, yeah. What I'm going to do is destroy this one and then not push and then just redo it later. So in homework 2, you're going to modify the file. You're also going to add a new one, but I'll skip that for now. But at the end, you're going to say like homework 1 submitted or something here. Right, and then click commit. Right, so again, so that made revision 3, but now we also have revision 2 that's kind of in parallel to it. So what's going to happen if I try to push right now, it says, anyway, okay, I think a new version came out of this. It gave me a different message before. But anyway, you'll see something about, see this for help about pushing new heads. And the reason for that is, again, we have these 2 versions that both claim to be the most recent, but they're they're not. One has to be the most recent. So again, so the way you resolve this is you have the one you're modifying, so basically the homework revisions that you make, and you want to incorporate these changes that I added from lecture. You right click this one, and instead of saying update, which just changes the state of the files on your computer to that revision, instead you say merge with local. So that's going to merge with your current working revision. So it's going to merge version 2 with version 3. So you should see clean here, so that means there's no uncommitted changes, right? Everything's been committed to some revision. And then you click next. And again, there shouldn't ever be conflicts when you're merging in things that I commit. If there are somehow, I apologize, and I'll help you get through it. But then last step is you click next, and you can just leave this at merge and then say commit now. And now what we'll see is we got a new version, version 4, but there are no changes here, like otherwise we'd see it here. All this is basically a combination of this version with this version. And again, because there's no merge conflicts, no two, like the same file wasn't modified in both of those versions, they just kind of mix together and create a new version that is just the combination of those two things. And again, once you see that there's only one single version at the top of the graph, that means you're good and you can push to your repository. Now I'm not going to, because I would kind of trash the central repository, so I'm not going to do that. But for your forks, it's fine to do this kind of thing. So actually, yeah, what I'm going to do is, so if you destroy your repo for some reason, you want to just kind of start over with whatever the current state is on Bitbucket. Easiest way is just go to this source folder and then UGV course. And the reason you know this is the head folder is again because it has this .hg in it. So this is kind of like the main folder of the repository. So if you just go up one level and delete it, now it's gone. Now you can just clone a new copy just like you did the first time you did it. So you come into Tortoise HG, but if you notice this is still here if you do that. If you try to double click it, it says it can't find it. So what you want to do in this case is right click, remove from registry, so it doesn't show up inside there. And now it's basically back the way like it was when you guys started. So then you just go file, clone repository, just like from before. And again, yours is going to be your username and UGV course, right? But I'm cloning the actual one, and then for destination, ROS source. Okay, so any questions on that? Again, so with this video, you can at least go back and kind of replay what I did, so you don't get, so if you get stuck, you can always just watch this again. If I have time, I'll go through and kind of index the lecture videos, like say, you get 15 minutes and 30 seconds, we started talking about this. I'm going to try to do that, so it's not just one big hour-and-a-half long video you have to skip around through to find what you want. I'll definitely do it by this weekend, if not sooner. So. Okay, so let's actually look at what I pushed in here. So we have the CPP and header files. Those were the actual programs that we were writing last time. In addition, I have this mysterious CMake list that tells the compiler what to build. And again, we'll look at how this works a lot more when we get into ROS, because ROS also uses CMake for all its building. And then there's this kdev4 file. So this is like the project file. So this is what you can open up in kdevelop to actually get the whole environment set up and everything. So if we go into kdevelop, sometimes you might see this screen instead. So you can just click the projects tab to open up the projects. And then you can say right click, open import. and then navigate to where that kdev4 file is. That's in ROS source, EGV course, CPP example, and kdev4. So it's going to bring up the configuration window. Everything should be good by default. And we have where we left off last time. So what we're going to do is kind of finish these two examples. The first example, if you recall, we just parsed, well, not even parsed it, but just listed out all the arguments that were passed into the program. Next, what we're going to do is actually parse them and just kind of multiply two numbers together, just as a really quick example of how you can actually parse the inputs into numbers. So what we want to do is pass two numbers into this program, and then it'll just return the multiplication into the terminal. So that means we should only accept two arguments, right? So the first thing we should do in our program is filter and just say, okay, if there's two arguments, we're good, continue. Otherwise, the user is inputting an incorrect number of arguments, and we should stop. So who remembers from last time how many arguments are passed in by default? Like if you just run the program, how many arguments are being passed to it? One. Yep. And what is that argument? Yep, the path. Yep, the path to the executable that you ran is by default the first argument. So, given that, what do you think we should do here to test if there are two arguments being passed, as two numbers being passed into this program? How can we check for that? So we have to remember what these two arguments into main are. What's argc? Number of arguments, and then argv, yeah, it's a pointer to an array of strings, which each one is one of the arguments. Right, so if argc is 2, that means there are two strings that this is pointing to. Okay, so what is argc going to be in the correct usage of this program with two numbers coming into it? 3, yeah. So what we can do is say if argc is not equal to 3, right, then we put a little message here, printf, saying incorrect number of arguments. All right, and then we can say return 1. So what this does, it stops the program, right, because it leaves the main function. So this whole program will stop at this point. And because we're returning a non-zero value, it indicates it's an error. All right, so returning 0 means it closed successfully in a controlled fashion, but returning 1 indicates, again, there's some error. Now, if it is equal to 3, we actually want to parse those two arguments and then compute the multiply. So that's where the C standard lib header is for. This provides, again, like I said before, functions to parse these string arguments into numbers without having to do it manually. So let's make an int a. So this will be one of the multiplicands. Say standard a to I argv. So if we want to access the first number that we're putting in, which argv index should we put here? 1, yep, because 0 is the path to the executable, right? So the actual first argument is 1, yep. So now, for the second, So for the second one, we'll call it B, and this will just be number 2. And then finally, C is just A times B. And then all we're going to do is just print that out to the terminal. So what should we put here to print out C? %d, right? Because %d expects an integer value, which is what C is, so that's good. And then put our new line so we don't have issues with that. And then C is the argument. And then return 0. So this should work. So to build, we just click this build button here. Yep. Oh yeah. So so I think what this stands for is argument to integer. I think is what this this is what the name comes from, I believe. Well, argument. So A is an argument, and arguments are usually strings, which are coming from argv. Yeah. So now another thing about kdevelop is if you hit control space while you're inside of the parentheses of a function, it'll come up with, well, this is a bad example because there's a lot of, okay, I'll show you guys more about that later. Essentially, A to I passes in a char pointer, char star type, and then converts whatever that string is into an integer, if it can. If you pass in a non-alpha, or pass in an alphanumeric thing, then it does something. I'm actually not entirely sure. But again, argv is a char double star, right? So A to I takes in just a char single star. So when you use the array notation, you're kind of dereferencing this pointer into the char array, and then what you get out is just a char star. So you do that with each one, and it returns an integer value for each of those. Okay, so then when you click build, you should see that it built our target correctly. And then again, there's two ways of running executables. One is within the IDE itself, and it uses this as the terminal. The other one is again to use go on the actual Linux terminal and run it. So the way to do it inside the IDE is go run and configure launches. And then CPP example should be there. And we have our project target. And then again, the arguments is where we want to actually put our values. So in this case, let's give it correct numbers, 7 and 5, right? And you separate them by spaces. Okay, and then current launch configuration should have our CPP example. So now once that's all set up, then the actual execute button will run that particular program. All right, so there's our argument list from before. So first argument's the path to the executable. Second and third are our two multiple cans. It got past this check, right? Because argc is equal to 3, and it hit here, which gives us our 35. So it works. So again, to do that from the real terminal, you first have to change your folder into wherever that is. So since we're starting from tilde, which means home, right? We say cd desktop. Keep doing that by reflex. I'll show you that trick later. Desktop. Or no, it's not on the desktop anymore. It's in the repository. It's in ROS source, UGV course, CPP example. Right, so notice how I can just keep putting slashes and go through all the folders. Right, you hit enter. If it exists, if that folder exists, it won't tell you anything, it'll just switch to it. So you can see that we're actually in that folder. And how do we show what's in this folder? What's the command? ls. So that'll show everything that's in here. And this isn't where our executables are, right? They're in this build folder. All right, so we can say cd build. And there's our two programs, so CPP example and factorial. So now how do we run it? Again, period, which means this folder, and then CPP example. Because again, you have to pass a path to a executable, otherwise the terminal assumes you're running a Unix command if you just type the name itself. I forgot to put the arguments in. All right, so now we listed our one argument, and then it failed that if check. So now we get this correct number of arguments, and then it stops. I also forgot the new line here. All right, So after you save, you click build, and now it's up to date. So now if we run the same thing again, so here's a very useful thing with Unix terminals. Instead of typing everything over and over and over again, you hit the up arrow, and it puts, you can keep hitting the up arrow, and it just cycles through your past commands. So it's not quite as nice as the MATLAB command window. Like if I type something and hit up arrow, it doesn't, it still loops through the past history, whereas in MATLAB, it would only loop through the commands that started with whatever you typed. So it's not quite as nice as MATLAB, but it's still really helpful. So we can just hit up arrow to get back to our CPP example and run it. And now we have our new line. All right, so that's pretty straightforward, but key to understand. Make changes, save, build, and then you can run it again. Okay, so now if we actually put some real numbers in here, like 2 and 9, we should get our result as 18. Now this is, I'm actually curious to see this. I don't know what happens if you do this. Okay, 0 apparently. Okay, so if you pass in alphanumeric strings into A to I, it comes back 0, apparently. Okay, so that kind of makes sense to everybody. All right. So now let's go over here and finish our factorial example. And we'll start by first reviewing what we did last time. So the first thing we did is we made the header file for the factorial class. And I kind of briefly went over what this is. This is what's called include protection. So if ndef means if this macro has not been defined yet, which it hasn't on the first time through, then you compile everything that's between if and ndif. Now the first thing that happens after that is it defines that macro. So that means the first file that includes this is going to actually have the header information. Second one won't duplicate this, which prevents name conflict. So if you have two source files including the same header, you'll have a name conflict. All right, so what this does is it prevents all of that from happening at all. So this is basically any header file you see on the internet will typically have something like this in it. Next thing we did is we put the class inside of a namespace. And again, the reason for this is forward-looking to when we start doing ROS programs. It's typical practice to implement all of your ROS code inside of a namespace that is the same name as the ROS package itself. Again, the point of that is for modularity. So if someone else makes a class called the same thing that you made, you won't have a name conflict because it's in a unique namespace. Okay, and then finally we defined our factorial class. So the key thing to remember is that every class has to have a constructor function, right? That constructor function has no return type, right? Not even a void, just nothing. And that function name has to match the same name as the class itself. We also made a public method called compute. So this is what we're going to call from our main program code, right, to actually execute the computation of the factorial. But then internally, we're going to use this mult function. So we don't have to call mult from where we're instantiating the class, right? But this compute function is going to need to use it. So that's why it's a private method as opposed to a public one. We don't need it from outside the class itself. And then our private property n is going to be the actual value we want to compute the factorial of. So again, notice that in the header file we don't actually write any code. All we do is provide definitions for classes and include any header files we need, which again we don't need it for this kind of simple example, but when we get to ROS you'll see we'll need a lot of header files. Now over in the CPP files where we actually implement the functionality of the class, so over here it has to include factorial.h, so it has that definition that we created. And then, because the definition is inside the namespace, we should always put our implementation inside the namespace as well. Here's our constructor function. takes no arguments and just defaults it to a constant of 3. So in its current implementation, this is really a 3 factorial class, not just a generic factorial. We'll fix that later. And then compute, we just implemented the factorial in a very simple way, right? Just keep multiplying the result by 1 less every time until we get our result. And again, these 3 lines are all equivalent, right? We have result equals result times n minus I. C++ gives us the shorthand times equals, which does the exact same thing as this. Right, when you say result times equals a number, it takes the current value in that variable and then multiplies it by whatever's on the right side. And then again, just to show how private methods are used in a class implementation, we did the same thing with this mult function. It just multiplies 2 numbers. So is this clear how this works so far? Okay. So then when I noticed that it was like 15 minutes late, which again, sorry, we were writing the main program code to actually use the class. So this first we have to include the header of the class, right? So we have all the definitions. Then the first thing we do is instantiate the class, right? And again, because the constructor has no arguments, we just don't put anything as inside of parentheses here. And then we just compute the factorial value by calling the compute method. Right, so this, as soon as the program hits here, it goes and runs this function, returns the result, and that goes into this factval variable, and then we just print it out to the terminal. Oh, this is the variable name. This is, the instance name of the class. So this can be whatever, right, as long as you're consistent with it. This is just like a variable name. So just like how I could say like int a, right, this a is equivalent to this. It's just the name of the variable. You can call it whatever you want. Yeah. Okay, so now if we go over and configure our launches, I think it's still, for some reason it's not giving us our factorial example here. Still. All right, anyway, still haven't figured that out. But anyway, we're gonna run it from the terminal anyway. So again, so if we go back to our build folder and type ls, we see that our factorial example is there. And if we run it the same way, /factorial example, I really should show you guys that trick that I'm doing, so I don't have to keep doing that. It gives us 6. So again, because it's a hard-coded 3 right now in the factorial, 3 times 2 times 1 is 6. Okay, so now let's make this a little more interesting and actually have it be a variable, like have us be able to actually change what number we're making a factorial of. So to do that, we're going to demonstrate what happens when you add arguments to the constructor. So now there's 2 ways to do it. We can leave this empty one and add another constructor, which we'll get to in a second. But for now, we'll just add an argument. So int n. So we're going to configure it at startup, what the number should be. So now we have to make another change somewhere else, right? We can't just change the header file, right? We go back here, and we see it. We still have empty constructor here. So now let's pretend we overlooked this and tried to build it. What you'll see is something like prototype for factorial. Factorial does not match anything in class factorial, right? So what it's doing is, because in the header file it's looking for this kind of a constructor that has 1 integer argument, it's not finding an actual implementation of that, right? It's not seeing in this file any constructor with a single integer argument. So if you see something like, if you see prototype in an error, that means the header prototype of the function, which this is what's called a prototype, just kind of the return type, the name, and the arguments, but without an actual curly braces with implementation. That's what's called a prototype. So when you see error prototype in the error message, that means this is different than what's in the actual code. So it's a clue to figure out what these problems are. So we just all we have to do is just add our int n here. And now it should compile. Oops. Oh, okay, that's another one. Now back in our main program, our constructor does have arguments, right? So now we actually have to put something in here. So say 6. Now if we build, it works. Now I haven't really actually done anything yet, right? I added this argument to the constructor. I added it to the implementation of that constructor, but I'm not using this yet at all, right? But it's pretty simple. Instead of just hard 3, you say n. Now again, a little bit on this naming convention. So the reason this has an underscore after it is because it's a private property of the class. So again, this is a ROS convention. Probably some other C++ style guides call for it as well. But it's a way of different, when you're just looking at a bunch of source code, if you see something with an underscore after it and you're aware of the style, you know that, hey, this is a private property of this class. Also, it lets us do things like this, where we can set initial values for things in constructor. We can say n equals n, or kind of keep the names similar. At least I found that a helpful byproduct of it as well. Okay, so now if we go and run it, 720. So this is 6 times 5 times 4 times 3 times 2 times 1. Right, apparently 720. So that's clear to everybody. So again, so if you don't have constructor arguments, you don't have to put anything in parentheses here where you instantiate the class. But if you do have constructor arguments, you have to put something there. Now here's one more thing that we're going to look at before we move on, and that is what's called overloading the constructor. So let's say we left our empty constructor there as well. So normally this is a bad thing to do, right? Having two functions with the same name. Right, if you did this in a normal, just straight source file, it wouldn't compile. It'd say you have two. Well, no, it would still work actually, but this looks weird to some, unless you're familiar with how overloading works. But it's actually quite simple. Essentially, 2 options for the same function. So if in the instantiating code we don't provide parentheses arguments, it'll run this one, and if we do specify initial conditions, it'll run this one. You don't have to worry about, you don't have to make 2 different functions with 2 different names. You can just call them the same thing for readability's sake and just pass it different arguments, and it handles it automatically. So what this means is back in our source file, we now have to implement both of these constructor functions. So in addition to this one, we also need to implement this one with no arguments. And in this case, we'll just have our old 3 value here. Okay, so now to demonstrate kind of how this is useful, if we go back to our main program, we'll leave this as it is, but let's also make a second instance of the class. Call it G and not pass it arguments, right? So we'll call this factval1. Run g.compute instead. So pretty clear what's going to happen here, right? Factval1 is going to contain 720, right? 6 factorial. Factval2 is only going to contain 6, right? Because that's what the argument list constructor is going to set the value to. so save, build, all green's good. Come back to the terminal, run factorial example, and we see our two values. All right, so this is a very fundamental concept, so we're going to be seeing this kind of thing a lot when we do ROS. So I just kind of wanted to give you guys a really simple one, just as a baseline, so you can get the fundamentals down before moving on to more advanced stuff. So any questions on anything? Okay. So we've been talking about ROS for a long time. Now let's finally get into it. So these slides are already up on Moodle. You might have seen that already. So if you've gone through them, nice work. But I will also go through them here. So we're not going to go over this all today probably, but start digging at least. So these slides, we talk about common terminology that we use in ROS. I think you've probably heard me refer to things like packages, and it's probably the only thing I've really said so far in much detail. But there's a lot of other common terms that you need to understand so that when I talk to you guys about it, you'll know kind of what I'm referring to. So we'll go over that first. And then the components of a ROS package. So every ROS package in existence has a couple of things in common with each other. So we're going to talk about what those common pieces are and how they are used to configure what the package does. Then we'll go through kind of a procedure of creating a workspace folder, creating a new package, putting code in it, and then writing what are called publishers and subscribers, and then also service servers and service clients. So we'll go through here, and if I'm going a little too fast or you don't understand something, just interrupt me and I'll answer your questions. So a workspace is a top level folder where all of your ROS components are stored. So again, in our case with the virtual machine at least, or actually any computer that you ran the setup script on, your ROS workspace is the ROS folder. So key components of a ROS workspace are the build, devel, source, and this .catkin workspace. So if you see these things in a folder, that's your workspace folder. Everything you're going to do, the whole class is going to be inside this folder. So now a package is some collection of ROS programs and libraries. So typically what's done is one package kind of has one set of functionality. So for example, there are a couple different SLAM packages, mapping packages essentially. There's another package that has just common path planning algorithms built into it. Right, so essentially what a ROS package is just a modular collection of libraries or programs that implements a specific function. So again, for example, when we do homework 2, you'll be making a package that's called homework 2, and inside of there will be all the programs that correspond to homework 2. Right, and homework 3 will be a new package, and etc. And then when we get to the second half of the class is when we'll start using some of those open source, like the mapping packages from the community contributes to and everything. Okay, and then node. So this is just a single program that runs and interacts with other nodes that are also currently running. So basically, this is kind of a really abstract drawing of how ROS is set up. So you have your workspace that encompasses everything, and you have, in this case, 2 packages. Each package compiles some number of nodes. So this first package actually has 2 independent programs that can be running at once, and the second package also has one. Right, so these 3 are, so basically nodes are the kind of like the individual component of a ROS system. You can have any number of nodes running at the same time, and they communicate with each other using topics and services, which we'll get to pretty shortly. So what a topic is kind of a publisher subscriber channel of communication between 2 ROS nodes. So what this means is that any node can kind of broadcast a topic, and any other node that is interested in the data that's on that topic subscribes to it. So that every time one node publishes data onto that topic, the other ones get notification essentially that there's data there, and then it reads it in. Right, so it's not point to point, right? It's basically one node sending data to everybody, and whoever's interested can listen to it if they want to. A message is the particular data that is being transmitted over that topic. So topics and messages are two completely different things. Topic is the channel of communication, right? This is how the method that the data gets places. Whereas a message is the particular set of data that is being transmitted. So you can think of as a topic is kind of like UPS. It delivers packages from point A to point B, and a message is the particular package you give to UPS to drive somewhere. Well, it's not quite the same because again, it's broadcast, but it's the best thing I could come up with sitting here. So I guess that's a very important thing to distinguish. Topics are the channel, messages are the actual data getting sent. Now another methodology for communicating between two nodes is a service. So this is kind of a point-to-point, on-demand method of communication. So essentially what happens here is one node says, I have a service, like if you give me this, I'll return with something else, right? And then any other node at any time can request that service. But the data isn't broadcast to everybody on the whole ROS system. It's just particularly responded to whoever called it. So these are the two main ways of communicate. Well, actually, the two only ways that nodes can communicate with each other. So now, deciding which one's which depends on your application. So typically, topics are used for periodic data that gets sent at a very particular rate. So, for example, you have like a GPS receiver, for example. There will be a node that receives all the raw data from the actual sensor. It'll package it up into a nice ROS message, and then it'll advertise that topic. And anybody who needs raw GPS data will subscribe to it. And then it'll keep publishing every, whatever, 10 hertz, 5 hertz, whatever rate the data comes from the GPS. So that's an example of when you'd use a topic. So basically for something that multiple nodes will need, potentially, and for something that has to happen repeatedly. Services, on the other hand, again, are used on demand. So a good example for this is you have a mapping node that you're driving a robot around a building, and it's building a nice looking map of the whole area. And now something else wants to snapshot that map and either save it to a file or do something else with it. So your mapping node will advertise a service that would save the map. Right? So then your node says, okay, I want to save this map. And then the mapping node takes a break from whatever it's doing, snapshots the map, and returns whatever relevant data for it. So that's a one-off. Like, it doesn't have to happen like at 10 hertz or anything. It's kind of whenever, right? Then you'd use something like a service. So that kind of makes sense, like when you use a topic versus a service. Okay. So here's an example runtime configuration of ROS. In this case, we have 3 nodes, 1, 2, and 3. So again, these are all independent programs that are running at the same time, being managed by the core of the ROS system. So again, ROS stands for Robot Operating System. So it's not like a computer level operating system like Windows or Linux, but it's kind of a small operating system that just manages the runtime nodes and also manages all the piping and underlying infrastructure to do all the communications. So in this case, node 2 is publishing data to some topic called topic number 1, and node 1 is subscribed to that topic. So anytime node 2 puts data out on topic 1, node 1 is going to get a interrupt essentially, and then can receive that data. Likewise, node 2 is also publishing data to topic 2, but in this particular case, node 1 and node 3 both need whatever data is on that topic, so they both subscribe to topic 2. So whenever node 2 publishes data here, both node 1 and node 3 get interrupts about that and can get the data from it. Yep.
How are the interrupts prioritized?
Essentially, yes, everything's time-stamped on the system, so whichever one happens to get published first immediately triggers the interrupt, essentially. But again, it's all managed by the core of ROS, so you don't, like, you can't set priorities or anything. It kind of has managed it for you. So again, so implementing asynchronous programs like that is, just operating on interrupts. You can do that in certain cases, but as we'll see later, most of the time you set up a timer to do all your processing in a loop, which we'll find out. But yeah, some simple things you can do purely asynchronously, which would be our first couple examples. But then probably next week we'll get into timers and how we can set up that so that when you're receiving multiple messages, you can be processing it at a regular rate instead of relying on which one came in first. Okay, then finally node 3 can be publishing a topic 3, node 2 subscribes to it. So basically there are no restrictions on how this works. You can have one node publishing to a topic and like 100 nodes subscribing to it. Right, so again with topics it's just purely broadcast, publish, subscribe model. Anybody who's interested can listen in on that data. So now there's a very handy visualization tool built into ROS so that you can see what the current runtime system looks like, and it's called RQT Graph. So all you do is open up a terminal window, type RQT_graph, and it comes up with something that looks like this. And this is a dynamic graph, so if you run nodes after you run this program, it'll automatically add itself to the graph. And basically all the ovals are nodes, so basically separate programs that are running, and all the rectangles are topic names, and then the arrows show who's publishing and who's subscribing to it. So in this case we have ROS bag, which I talked about the first class. This is how you record and play data back to the system. So the bag is publishing to all these topics, right? So basically these are the topics that I recorded earlier. Right, and then GPS example, which is one of the things we'll be writing later in the class, subscribes to the GPS velocity and the GPS fix, right, and then is using that to basically project out a GPS path, so basically the history of where we were, essentially. Right, so this is a very valuable tool because sometimes what will happen is one node will be publishing to a topic and this one will be subscribing to a different one when they're meant to be the same, right? So let's say if I, instead of GPS vel, I was subscribed to just like vel or something, you would see one box for GPS vel and another box for just vel with that going into here. So you'll see a disconnect, very clear disconnect between two nodes, and that's how you can tell that something's wrong, right? If your data isn't getting from point A to point B. So keep this in mind, it's very helpful. So makes sense so far? So this is kind of, so we've gone over so far is just how ROS runs, essentially. It's a bunch of nodes and they communicate with either topics or services. So inside every ROS package there are going to be two files. One is called package XML and the other one's called cmakelist.txt. So package XML describes basically all the dependencies for that package. So your ROS package can depend on other ones. So so if someone built a library in their ROS package and you want to instantiate a class that's inside that library inside of your package, you have to list that other package in package XML as a dependency. And again, we'll see this a lot as we go forward. So cmakelist functions the same way as our little simple one that we just did for the factorial example. It basically inputs commands to cmake, which is what ROS uses to compile all of the nodes. So it basically package XML lists the dependencies that that your package depends on. CMake lists instructs what and how to compile the nodes that are in your package. So package XML is obviously an XML format, which again, if you don't know XML, don't worry about it, because I didn't either when I started working with ROS, and I'm still here to talk about it. So we're just going to go through this really quickly. So at the top here is XML version. So this does nothing really. What this does is tells text editors what kind of XML version this is, so that it can add color highlighting to aid in editing it. And then everything goes inside of a package and /package tag. And then we have a name, version, descriptions. All of these are required. They have to be here. But the description, version, maintainer, and license, these are for when you want to basically release your package into the ROS community, into the build farm, to actually build binaries and distribute them to everybody. That's when it uses these things. So basically for this class, we won't be releasing anything into the ecosystem. So you can just, the only really important thing here is the name. This has to match the actual name of your package, but the version, description, maintainer, and license don't matter. You just leave them at, these defaults, it's fine. This build tool depend, this will always be the same for every package. So catkin is kind of a layer on top of CMake that is ROS specific. So basically ROS has custom CMake commands essentially that go on top of CMake, and that's called catkin. So it's always going to be, so this is always going to be the same. Now here's the part where you're going to change depending on what you're writing. These build and run depends. So all these names, geometry messages, ROS, CPP, TF, these are other ROS packages that this package is going to be dependent on, because either, as we'll get to later, message types are defined in those other packages, or there are classes, or excuse me, libraries compiled in those other packages where we need the classes out of them or something. So basically build depend and run depend are what you're going to change in this file throughout the class. Everything else, except for the name here, you can pretty much leave alone. So this is kind of what I just described. So. And then there's so build depend. So this is a package that depends on during build time. It's when it's compiling, right? Run depend is something that it needs at runtime. So again, 99% of the time you'll have both a build depend and a run depend for a given package. All right, so if we go back here real quick, you'll notice that there's a build depend for geometry messages and a run depend for geometry messages. In certain situations, you don't need a run depend, but you need a build depend, but it never hurts to have both. It never causes any issues. So if you're ever in doubt, just put both and you'll be fine. Then export, if you look at some of the code that I provided to you in that UGV course code, you might see me put something inside the export tags, but I don't think anything we're going to do in terms of homework or projects, you'll need to do that. So, so most of the time they'll just be empty. Okay, so obviously you need to see some examples to see how this works in a functional sense, but any questions on that before that though? Yeah.
I just have a question in the XML file. You specify like a path. How does it know, does ROS know where to find those packages?
Well, what it's going to do when you go to compile your ROS workspace, which we'll see soon, is it searches your whole workspace folder. It starts here, goes into your source folder and searches everything recursively until it finds every package.xml file that it can see. Right, and wherever it finds those, it identifies that as a ROS package and then runs the CMake on that one package. So you don't have to, all this is automatic in the background. All you have to do is just make sure you have your package XML and CMake lists in each of your packages. Okay, so now again, CMake list is how we're going to tell the build system what to do with our source files essentially, and actually compile some programs. So at the top you'll see CMake minimum required. I think it still says 2.83, so you'll never change that, it'll always be there. And then project, so this has to be the same name that you put here, which I don't know why I didn't do that in the slides, but this name has to match whatever you put here in project inside of the CMake list. The next piece is called find package. So this is where you basically, this is how you kind of link all of your things in your package to your dependencies. So find package, catkin required components, that's always going to be there. And then you make a list of all of your package dependencies. And this list is going to match this list. So if you have geometry messages, ROS, CBP, and TF in your package XML, you're also going to have those three things here in this find package command. The next thing that has to be there in your CMake list is this catkin package with empty parentheses. Again, if you do fancier things with like exporting libraries and things, you'll actually put stuff inside of these parentheses. But I think if not all, definitely most of the packages we're going to write in this class, it'll just be empty parentheses like this. You just have to have this in your CMake list. And then this looks familiar. This is kind of what we had to do with our simple C++ example. Whenever we want to actually create an executable program to run as a ROS node, we put an add executable line. The first argument is the name of the executable file. Right, so this is going to be the name of that executable that we would run in a terminal, for example. And then after that, you list all the source files that make up that executable. So in this case, we'd have two files. One's in the source folder called file1 CPP space. Another one is also in source called file2. So basically compile these two source files together and put them in one executable in this case. Now, these three lines do a lot. So what this does, it target link libraries. We put the same executable name here. So this is going to link our program that we just compiled to the catkin libraries. So basically, this catkin libraries contains all of the core ROS components, so everything that allows us to publish messages, subscribe to messages, advertise services. Everything that, all the core ROS components are all inside this catkin libraries. So if you forget to put this in here, you'll get a lot of errors saying, I don't know what ROS is, right? Because you're not linking against the libraries properly. So that's what this last line does. And then again, you can have any number of nodes compiled in your node, in your, your package. So you can have as many of these add executable lines as you want. So if we put it all together, this is what a complete CMake list file will look like. So again, we have the minimum required version at the top. We have our project name. So again, this has to match the name of the package itself. Then you list your other catkin package dependencies. Declare that this is a catkin package with this line, and then add an executable. And this is a complete CMake list. Okay, so now most of this stuff is done for you by the setup script. Essentially what this goes through is cd tilde goes to your home directory, right? mkdir basically makes a folder and it creates that ROS source folder. And then what we haven't done yet though is this catkin make. So if we go over to the terminal, so we say cd tilde, which goes to our home directory. If we ls, we see our ROS folder there. So we can cd to that. And again, your ROS workspace folder is going to have build, devel, and source. So basically the folder that has these three things in it is your workspace root directory, and this is where you have to be to run the compile command. And the compile command is called catkin_make. So what'll happen, well, let me do something else here. No, it's fine. So what this will do is, again, goes through all of the ROS packages that it finds, and it finds them by identifying the package XML file in each folder, and then compiles the source files inside of it according to the instructions in CMake list. So right now we have absolutely no ROS packages in here. Homework 1 is just a text file, right? That's not a ROS package. CPP example is not a ROS package, right? There's no package XML in here. So catkin_make does nothing, apparently. But what it does do is it automatically generates this build and devil. So like if I got rid of these, for example, all right, and come back here, up arrow, so again, cycle through the commands, hit catkin_make. So now it'll go through here, it'll put these back in, right? And now what it's doing is it's compiling all of the things in the other folder. So again, because I deleted that build folder, I deleted all of the binaries of all of these packages, right? So now that those aren't there anymore, it has to go back and actually rebuild it. So again, if on your computer you do the same thing, delete the build folder and then run catkin_make, it's going to go through and compile all of the simulation code. And what you'll notice is that this percentage will gradually increase, and when it gets to 100, it'll be done. Pretty straightforward. So this will take a little bit, of course. So basically everything I showed you guys the first class, that's all the stuff that's in here. So all of those car simulations and maze navigation simulations are all getting compiled right now. And while that's going on, we'll go here. So now, again, this is all done for you with the setup script, but there's a file called .bashrc that's on your Linux computer. And if we go and check out what that is, so that's in your home folder. Come on. So there's this .bashrc. So again, remember, everything that has a period in front of it is a hidden file. So this is why I have it default to show hidden files, because you have to sometimes get into this one. So what this is a bash script. So essentially scripting Unix commands is essentially all it is. And the special thing about this one is bashrc. This is what runs every single time you open a terminal window. It automatically runs this script. And what it does is it configures various environment things for your terminal, so it loads all the default functions and everything. So if you go to the very bottom, you'll see a couple interesting things. This one here, home. So source is essentially, it's kind of like include in the C++ file. It goes and basically copies whatever is in this bash script and run it. And what this does is it sets up the ROS environment in that terminal that you open up, so you can run things like catkin_make. Like if that wasn't there, it wouldn't know what catkin_make is because it hasn't loaded that command. Right. So again, so if you open up your bashrc in your VM or your computer after you run the setup script, you should see these things down here. If that's correct, then if this is here, that means it ran correctly. Okay, so now let's actually create a package and do some simple things in there. But let's talk about how that goes about first. So all the packages you're going to write are going to go in your src folder. Right, so don't put it in the root of the workspace because it won't find it. It always looks inside of the src folder. And then inside of there you can type make dir, make a directory, and call it something. So this will be the name of the package that you're going to create. And then inside of that folder, you want to create your two fundamental files, right? CMake lists and package XML. This is our bare minimum CMake list. So all this does is it has the required version, the name of the project, depending on ROS CPP, which is all of the core C++ libraries that allow you to publish and subscribe to messages and things like that. And it says that, hey, I'm a Catkin package, so build me. Right. So this is the absolute bare minimum CMake list you can have. So then what you're going to do is, depending on what you're doing for that package, you'll add whatever package dependencies you need, and then after Catkin package, put all the add executables for all the nodes that you're building. Right, so what you can do is start from here every time. So open these slides, copy this text into a CMake list.txt, and then go from there. Likewise, here's the corresponding bare minimum package XML. So again, this name has to match the package name, and build tool depend Catkin has to be there all the time. And then what you're going to change are the build and run depend. Right, so again, likewise, the only package dependency in here is ROS CPP. This corresponds to this list. So if you add something like geometry messages, like we saw in the example, we'd have to put that in this list, as well as a build and a run depend on geometry messages. Okay, so here's our first example of how to actually do something with ROS. So what we're going to do is write a node. It's going to subscribe to a topic that contains a string. It's going to add _123 to that string and publish it out on a different topic. So it's going to subscribe to a topic. When it gets a piece of data on that topic, it's going to add a _123 at the end of it, and then immediately publish it out on a different topic. So obviously you need to create a source file to do this. You can call it topic publisher. We'll do this in real life as well. Just want to talk about the higher level stuff first. So at the top of the source file, this is a very important one, include ros.h. So this is going to include everything that you need to publish data, subscribe to data, advertise services, call services. Right, so basically anything we're going to do this entire class is going to always have an include ros.h at the top of the file. And then another thing is we have to include the string message type. So again, a topic is just a vehicle, it's just a method of communicating between nodes, but the actual data on those topics are called messages, and each of those messages have different types. So again, in our particular case here, we're going to be subscribing to a string topic. So that means it's going to be string messages on a topic. So in general, actually always, you have to include the header file that defines that message type. So in this case, we're going to be subscribing to a standard messages string. So we have to put the header file for that message as an include. Next thing which we do is we declare a ROS publisher. So this is a class that interfaces to the core of the ROS system and actually manages the transmission of the data on a topic. So for implementing this in a single source file, like not in a class, you typically want publishers to be global variables for reasons we'll see soon. So this will be the stuff at the top of the file. And then just like any other C++ program, we need a main function, but we're going to do some new things that we haven't done yet. First thing is this line here, this ROS init line. So what this does is it registers this node with the core of the ROS system. Basically it says, hey, I'm a program I am running and this is my name, topic publisher. So inside of that function you pass the same argc and argv and then the name of your the runtime name of your node. Second line is what's called a node handle. So this is another class. It's called node handle. And this is the class that we use to interface with other things going on in ROS. So for example, we're going to subscribe to a string message. So what we do is we declare a subscriber class and we initialize it with this node handle. And the node handle has a method called subscribe. We give the name as the first argument, a buffer size, which we'll talk about some more in a little bit, and a function callback. So essentially what's going on here is we're telling the ROS system that we want to subscribe to this topic called topic in, and we want to call this receive string function every time we get a message on that topic. And then likewise, we want to publish out the modified string on a different topic. So pub string, which is our global publisher class instance, we initialize it with, again, the node handle, but we use the advertise method instead. And since advertise, you can advertise any message type you want, basically. It's what's called the template method. So inside of these angle brackets, you have to put the particular type of message that you're actually transmitting, which is in our case standard message string. And we put the name and again an output buffer size, which we'll talk about more later. And then finally, there's this ROS spin command. So in our two examples we just did, right, we ran a program and it just immediately stopped. Right, we multiplied two numbers, stopped. Compute them factorials, stop. In general, ROS programs should just keep running forever until you stop the system, right? So what this ROS spin basically does is it'll hit this line and sit here forever until the user kills the system. So if you've had some experience writing like microcontroller code in C, right, you'd have like a while one loop, which means it'll just kind of loop there forever. Right, so this is kind of like that. This is basically exactly like a while one loop. However, if you did put while one here instead of ROS spin, it'll just get hung there. It won't do anything. It'll just sit there in a loop forever. What ROS spin does that is special is that it monitors any topics that you're listening to. Right, so it'll sit there and loop and do nothing while it's sitting here. But as soon as the ROS system says, hey, you just got a new message on this topic in, it'll break from that and go service this callback function and then go back to just looping again. So you can think of ROS spin as a while one loop, but it's a special while one loop that listens to any subscriptions that are currently active and then servicing them when the interrupts occur, essentially. Does that kind of make sense? So again, so you don't have to put this here, but the issue is it'll just run and stop instantly, which in our case is not what we want, because we always want to just be listening to data and then doing something in response. Okay, so now this receive string function, right, this has to be implemented, right? This is what's going to run every time we get a message on the topic. So this is what's called a topic receive callback. So this is just like any other C++ function, right? You have the return type and the name. But now the argument follows a very consistent pattern. So even if this looks cryptic right now, there's actually a very simple pattern to it. You're always going to have a const. You're always going to have const pointer ampersand. And what's going to change is the stuff in between. Again, in our particular case right now, we're subscribing to a string message. So this standard messages string is what's going to change. So if we go to like an integer, for example, this would be standard messages int32 const pointer ampersand. So the key thing to remember here is what's going to stay the same all the time and what's going to change in your particular situation. So things that are going to stay the same are const and const pointer ampersand. Things that are going to change is standard messages string. And then MSG is just the name of the argument. You can call this can be whatever you want as long as you use it appropriately in the function itself. So this is why we talked about pointers last time, is that because every message that you receive is going to be passed into your callback as a pointer to that message type. And in general, actually always, messages are structures, right? So if you remember from last time, we talked about how you can define your own structure with like a float and a string and an int all kind of bundled into one structure. That's basically what a ROS message is. It's a structure of data. So to get at that data, since it's a pointer, we use the arrow symbol, right, instead of the period, because it's a pointer. So to implement what we want to do, we declare a standard messages string. So this is a message, right, a ROS message structure. We call it new string. And then new string.data. So there's a field in the structure called data, which is a regular actual C++ string, which is important to know the difference between. Standard messages string is a ROS concept, is a ROS thing. It's a ROS message structure, whereas the data field inside of it is actually the same kind of strings that we talked about last time. So new string.data equals message arrow data, right, because MSG is a pointer, and then we concatenate _123 to it. So this is another cool thing about C++. Concatenating strings you can do with just a plus sign, as opposed to in C you'd have to allocate the memory for the string and then copy the data into the appropriate spot in the array, right? C++, as long as you're dealing with the string object, you can concatenate with just a plus sign. So that's a little side handy thing to do. Okay, and then finally this last line here, we use our pub string, which is our publisher class, and we call the publish method the new string in it. So this is what's actually going to broadcast our modified string into ROS. So again, so any other node can subscribe to it and get our modified data. Okay, and the next slide is basically just kind of break down each chunk and describe what I said in words and actual text. So nothing too much here. Okay, and then the last step, once we have our source file written, now we have to tell catkin and CMake how we want it compiled. So that means we have to go into CMake lists and put an add executable line in there. If we don't put this in here, nothing's going to get compiled and we can't run our program. Right, so again, so the way this works is we say add executable. First argument is the name of the executable file itself. Second argument and any more after that are just a list of the source files that go into that node. So in this case, there's just the one. Right, so we list that there. And again, very important is the target link libraries with the same executable name and this $catkin libraries. So this is what links it to all of the ROS libraries, so that if we don't have that, our program doesn't know what a ROS node handle is, right? Because it hasn't linked to that library to get its definitions, essentially, right? So again, so any node that you compile for the class is going to have to have a target link libraries with it as well. So just kind of keep that in your head. If you're writing an add executable line, just know that you'll also have to add a target link libraries line. Those will never be separate. Okay, and then once you have your CMake lists edited, again, you go to your root of your workspace folder. So again, so wherever your build, devil, and source folders are, that's where your terminal working directory has to be, and then you run catkin make. And again, it can take some time, so you can have a sword fight on rolling chairs if you want to. It's doing that, and you shouldn't get fired. Okay, so we don't have time to actually do this, otherwise I'll keep you guys late again, and eventually you'll get angry with me. So we're going to stop there for today. So any questions, anything before we call it? Okay. There's no class on Monday, I think, because of Martin Luther King Day. So we'll see you guys a week from now. And if you have any questions getting the computers set up or you see some weird errors or something, just don't hesitate to email me. I'll get back to you very quickly.